Good morning. My name is Kimberly Pierce Dobson, Business Development Manager for TBC-Brinadd. I'm here in Houston, Texas, with a live broadcast of our technology webinar series. Today is the fifth session of 7, and we will be covering our DrillIn systems. We will continue our technology webinar series every Thursday at 10 a.m. through July. If you have questions or comments throughout the presentation, you can put them in the chat section or the questions down below, and we will respond after the presentation. Today we have speakers, Kim Tresco, our product line manager, and also our VP of Technology, Mark Luyster. Kim, the floor is yours.
Thank you, Kimberly. Hello, everyone. I'd like to thank you for joining us today. We want to start by sharing TBC-Brinadd's DrillIn fluids history and the advances in our drilling and completion product line. TBC-Brinadd started producing and distributing specialty production zone drilling, completion, and workover fluids in the early 70s, with the development of a completion fluid that involved a polymer and size salt mixture known as Thixsal. In the early 80s, our sized rock salts were being utilized in several novel ways for drilling and completing. Fluids and pills containing salt were used to plug specific zones temporarily and then removed with water. This technique was successfully used on over 400 wells. During this time, the success of the first horizontal test research well allowed the first producer to be drilled with size salt by Standard Oil in Prudhoe Bay. In the early 90s, a new polymer, FL7+, was introduced to address limitations like temperature stability of the conventional components in the original salt completion fluids. FL7+ continues to be a very effective fluid loss additive to this day. TBC-Brinadd continued to develop with new systems and additives that would perform in high-density brines while maintaining low solids concentrations. Our complete line of systems and additives are listed on the next slide. In addition to our specialty additives, which cover a wide range of functions in our loss circulations, we offer the complete drilling systems. Each have been used worldwide. The systems shown in red are the topic for today. We will go over DrillIn, Thixsal-Ultra, Ultramatic, and UltraPF. This slide gives you an overview of the applications and features for the 4 systems. From top to bottom on the first column, you'll see that the base fluid type ranges from divalent to monovalent to formate. Quick differences between each system. The drill utilizes no biopolymer gum. Instead, this system generates low-end viscosity due to the synergistic combination of starch and buffer. This unique characteristics allows for engineering ECD. Our Thixsal-Ultra system is for use with all monovalent brines and utilizes size calcium carbonate or sodium chloride as bridging agents. Our Ultramatic system incorporates an alternative bridging agent with a specific gravity of approximately 3.56. We offer a wide range of magnesium oxide bridging grades. These grades with this specific gravity can reduce total bridging concentration. This reduction allows total solids loading by 21 to 27 weights per weight, which helps reduce ECDs. Our UltraPF system was developed for use in formate brines. This system has enhanced LSRV and mitigates gelation in the formate brines due to the synergism between the starch and xanthan. All of these basic systems for these is effective in the environments listed above. However, with the introduction of specialty additives, these 4 systems can achieve an environment not checked, such as thermal stability. All systems can be used to build fluid loss pills, workover systems, liner runner systems, and injector systems where direct injection and mitigation of channeling occurs. Now, looking at how our systems differentiate in technology, each use a unique fluid loss control additive. We'll discuss first the drill system. TBCX600 is the starch of choice, highly branched. The molecular weight is similar to xanthan. It's cross-linked to reinforce thermal stability and shear. Pre-gelatinized to provide dual functions such as viscosity and fluid loss control. Our Thixsal system incorporates FL7+, which is cross-linked to reinforce thermal stability and shear. It's hydroxypropylated for resistance to biodegradation, which improves storage stability and increases solubility, which allows hydrate to and near saturated, even saturated brines. Our Ultramatic system utilizes broma FLA. It is a corn starch derivatized, partially depolymerized non-ionic to mitigate effect of the gelation from magnesium oxide. It's only partially cross-linked for thermal and shear stability. Our UltraPF system incorporates formitrol. It is a cross-linked derivatized starch to effectively function with xanthan gum and formate brines. Each starch undergoes a unique QC process to validate every lot to ensure we are giving the quality product performance needed. Now let's look at two of our systems further with the starch evaluation in each of these two systems. The first one we'll talk about is DrillIn. DrillIn, the first table, above table you will look at is showing the impact of a buffer on low shear rate viscosity to 3 different starch derivatives and a 4.5 pound per gallon calcium bromide. Evaluation was done with and without a buffer. The buffer concentration is a 1/4 pound per barrel. TBC-X 600 incorporated with or without a buffer does provide low shear rate viscosity and is stable over aging and shows no settling or separation despite the other 2 starches that either have total separation or gelation. As mentioned, DrillIn is a biopolymer-free system. Based on that, we did an evaluation with 3 different gums, looking at the yield, performance, and a 12.5 pound per gallon calcium bromide, focusing on do we have yield up front and do we have no separation or settling after aging. TBC-X 600 does perform with initial yield up front and maintains no separation or settling. The next system related to UltraPF system and the formitrol additive. The upper table we looked at a 12 pound potassium formate base brine with 22 pounds per barrel to differentiate performance of the starches, thus the ability to measure before as well as after. We are looking for yield of the polymer initially with nominal change after aging. Starch derivatives 1 through 4 have no yield up front, and it took time and temperature to achieve viscosity. PAC did provide yield up front, but temperature impacted the viscosity after dynamic aging. Formitrol proved and provided yield initially and maintained viscosity. The lower table, we were looking at the performance of formitrol, yield performance in formitrol in various base formate brines, starting from an 11.5 going to saturated 13.1. Again, confirming that we have viscosity up front without gelation and very nominal change after hot rolling at 250 degrees for 16 hours. Next, Mark will be discussing each systems further on their field performance and additional lab.
Thanks, Kim. These next slides hopefully will provide you some more detail about the 4 systems. First is our DrillIn system. This system generates the low-end viscosity without biopolymer gums, as Kim demonstrated previously, but more importantly, it mitigates gelation. It's cement tolerant. There's no treatment required. Thus, you can use it to drill out after cementing a liner or a string and continue drilling through the pay zone. Low field maintenance is only 3 products typically required: the starch, TBC-X 601, which is the buffer, which generates viscosity, and the calcium carbonate bridging grades. As shown in the table, density is achieved with the divalent-based brines, typically 10.3 to 10.5 up to 16 pounds per gallon. This promotes flexibility and yields same performance in low or high density brines. It's temperature stable to approximately 260 to 265. It provides the ability to formulate liner running systems as well as systems for workover, even recompletions. It's conducive for initial well cleanup. So you have the ability to engineer for completions such as passive ICDs, where pumping a breaker is limited. Due to the density of the base brine, which reduces total solids, in the absence of the biopolymer gum, these impart the ability to engineer the ECD for drilling narrow windows. The following is an example using data collected from a horizontal well. So this well was drilled with a 13-pound per gallon die drill system, used 35 pounds per barrel of bridging solids. The ECD target was 13.8. That was a less than 0.8 pound per gallon optimum with a 0.9 pound per gallon maximum allowed. So we drilled an 8.5-inch well bore starting at about approximately 16,480 feet to TD, and it was to remain within a 50 to 55-foot window through a Miocene target sand. From the first row in the table, the SPP reflects a pump rate from 500 to 550 gallons per minute at a controlled drill rate. From the ECD methods, there were two methods used. First, we estimated the ECD with software, and then we actually measured the ECD in the field with a gauge. The differences shown in the table are simply a snapshot at each depth. However, the average difference over this interval approximated 0.045 pounds per gallon, where predicted was less than the actual. This provided a level of confidence that the ECD as measured was accurate. The ECD ranged from 0.69 to 0.79, achieving the optimum target. The increase you see at TD is most likely due to the accumulation of drill solids, which increased to 1% by volume, where the increase in total solids was from 39 to 49 pounds per barrel. Next is our Thixsal-Ultra system. This system can be formulated up to densities of approximately 13.5 pounds per gallon. It's temperature stable to approximately 250 to 260 and up to 300 with stabilizers. As Kim indicated previously, this uses the cross-linked hydroxypropylated starch, and this imparts solubility and fluid loss control even in saturated brines. With the addition of xanthan, as shown in this table, this system is typically moderate to highly inverted and exhibits nil gelation with elevated LSRV. The images show examples of filter cakes from a saturated system that use 46 pound per barrels of salt. These are shown after a PPT with 5,000 PSI differential on a natural sand disk. The filtrate total after 30 minutes approximated 9.5 mils. The ability of the FL7 Plus to function in this saturated brine contributes in part to the relatively low fluid loss, thus the thin filter cake you see in these images. The Thixsal-Ultra system uses a myriad of bridging grades that we can supply. The table shows the diversity of these grades. First, the salt and halide grades are available as evaporate or rock salt. Thus, Ultrasal E for evaporate, R for rock salt. The difference is their purity. 99.9% for the evaporate, 92 to 96% for rock salt. The plug sal grades, also a rock type, function as bridging agents for drilling or fluid loss control pills. And last, we offer a series of calcium carbonate grades with purity approximately 96% or greater. As a note, TBC can grind any of these materials to a specific spec as well as coat to mitigate caking. Next is our Ultramag system. The difference is the specific gravity of magnesium oxide versus calcium carbonate, where the magnesium oxide is the bridging agent. This yields as great as 27% by weight reduction. This difference can fill the gaps with the liquor brines that are used as the base to achieve a higher density. So the Ultramag grades are unique as a bridging agent in that they are sparingly soluble in water and aqueous systems. Thus, they're non-reactive in concentrated brine. They provide dual function as a pH stabilizer and a bridging agent. In most systems environment, no buffer is required. These systems function from approximately pH 9.5 to 11. Magnesium oxide is soluble in acidic solutions, as is well known. However, it's compatible and degradable with breakers comprised of oxidizers, acid precursors, or chelates, as well as partially soluble in ammonium salts. These breakers do not impart secondary reactions that may cause damage. The image shows residual filter cakes that are nearly completely removed by these chemistries. This system can achieve densities up to 13.5 pounds per gallon with sodium chloride, sodium bromide base brines, and combinations thereof. No divalent brine is typically used, as there is in part some gelation. However, these systems are stable to approximately 275 degrees Fahrenheit. The primary components comprise standard biopolymer gum, the Broma FLA starch for filtration control, and the size magnesium oxide for bridging. This shows the bridging grades that we currently utilize. There are 7 grades available. I show them as 3 textural classifications: very fine, fine, and medium. This range provides effective bridging over a wide range of permeability as well as fractures. For example, 4-Darcy formation would equate to a medium pores of approximately 62 to 64 microns, whereby the bridging blend is easily optimized with the PSDs shown. On Mohs hardness scale, magnesium oxide is approximately 5.5. These grades typically exhibit a purity of greater than 98%. The impurities are calcium and silica oxide, approximately 1 to 1.5%. These grades are calcined, and this retards their reaction activity. As such, they function as a bridging agent versus a buffer. The next system is our UltraPF. As known in the oil field, formates provide a relatively wide density range, even up to 20 pounds per gallon, and temperature stability to 330, 360 with stabilizers. From the second and third bullets, formatrol starch, that Kim mentioned earlier, provides synergy and stability at the low ends. It enhances the LSRV and provides low fluid loss. The images show a 12.5 pound per gallon system that used 35 pound per barrel of calcium carbonate, 8 pound per barrel of formatrol, and 3/4 pound of xanthan. These were deposited at 250, and the low fluid loss control yields relatively thin filter cakes as exhibited by both a FAN 90 and an HTHP test. So formates are also known as inherently shale stabilizing brines. In the next slide, here's a small example that shows the results after dynamic aging systems for 16 hours at 150, where they're exposed to Pierre shale discs. These systems utilize 10 pound per barrel of formatrol and a 0.5 pound per barrel of xanthan. The reference for this type of test is oil-based mud, typically 99 to 100% SSI, thus the greater than 90% target. Note that high-density formates, such as 13.7, most likely never require an inhibitor, while lower-density systems may require due to the increased water. The rheology table for the UltraPF system shown in this is a 13.6 pound per gallon system. This included 1% drill solids. They were dynamic aged for 180. This shows the UltraPF system for 5 and 7 pound per barrel of formatrol, and both used a 0.5 pound per barrel of xanthan. The reference in the last 2 columns shows 6 and 7.5 pound per barrel of a cross-linked starch and 0.6 and 1.5 pound per barrel xanthan. Note the gels highlighted in red. You can see that they're all nearly flat for the UltraPF system, but they're increasing for the cross-linked starch. Also note that even when decreasing the xanthan, such as the 6.5 pound per barrel, while the gelation is reduced, the system is no longer inverted and the 6 and 3 RPMs are reduced. Next, I'd like to show you 2 examples of return perm, and we selected an open hole gravel pack and a direct injector. We selected these 2 examples as arguably they are the more difficult to clean up before execution in the field. So both of these return perm examples utilize our Thixsal-Ultra system. This Thixsal-Ultra system included 0.5 pound per barrel of UltraBrake M, which is our internal breaker. The system was designed inverted such that the PV/YP almost 3-to-1. However, the 10-second, 10-minute gels, 20 and 21, thus nil gelation. So to simulate cleanup of an open hole gravel pack, we used a 2040 gravel and a coupon of a premium sand control screen, and these were incorporated after the mud off on a formation sand pack. So first, the initial perm was established with 3% KCl. It was done for the pack as well as the screen. Next, there's a dynamic mud off performed for 8 hours as 4 hours dynamic, 4 hours static at 226 and 240. And 1,000 PSI system pressure was applied for both. This yielded 9 mils, where 160 mils was established as the maximum allowable. Then we applied the gravel in the screen and pumped the breaker. The breaker was retarded acetic HCl. We pumped it through the screen and the gravel, allowed it to static age for 4 hours at the bottom hole static temperature of 240. And last, the final permeability is measured again using 3% KCl. Note that the return perm percent for the formation approximates 82%. However, the screen coupon is removed and also measured to determine presence of damage, yielded 89%. The red arrow on the image on the right shows that the residual filter cake is nearly completely degraded or dispersed, which in part validates the use of the internal breaker UltraBrake M. And our last example is a direct injector. The objective for this simulation was to prove that direct injection could remove the filter cake without mechanically breaking down the sandstone. So the operator had to sweep this sand as opposed to mechanically breaking down the sand, which would channel the injection water. So first, we measured the initial permeability as direct injection. We used an 8.8 pound brine to approximate or simulate the density of the injection fluid. We established the permeability of this core is 200 millidarcies. Next, we mudded off with a 9.3 pound per gallon Thixsal-Ultra system, which also included 0.5 pound per barrel of our UltraBrake M. Fluid loss was conducted for 16 hours as 1:14:1. That's dynamic, static, dynamic at 175. We used 500 PSI system pressure. Next, the external acid was applied to activate the UltraBrake M. This was allowed to static age for 80 hours, as the 80 hours represented the approximate time until this well would be placed into injection. Next, we initiated direct injection with the 8.8 pound per gallon brine, and it required only 2 PSI to initiate flow. We continued for 20 pour volumes to confirm stable permeability. The direct injection permeability was 62% after the 20 pour volumes. We removed the core from the system, and iodine is used for confirmation of starch. It's applied from the top, penetrated the filter cake approximately 3 millimeters, as shown on the image on the left. Next, we took the residual filter cake, cut it in half, which is shown on the image on the right as a cross section. And note that the area contacted by the iodine is negative for starch, as the iodine remains yellow. If it's purple, this is an indication of the presence of starch. Note the residual filter cake in the lower right as indicated by the arrow. The absence of the milky white color is indicative of the absence of biopolymers. This again indicates of the conversion of the internal breaker, which subsequently degraded these polymers locally, as such a pinhole. With that, I'll turn it back over to Kim. She's got a few more messages for you.
All right, thank you so much, Mark. Kimberly, once again. So to go over, these are listed, our publications that are covered the products that we just discussed today. These are case histories. You can find these on our website at TBC-Brinadd.com. If you have any questions about our packaging, samples, or technology, you can always reach out to your contact or sales and marketing at TBC-Brinadd.com. Next week, our topic will be over our loss circulation systems. It will be at 10 a.m. as well. And then our last Thursday, we'll be covering our polymer breakers that break all systems discussed the last few weeks. Again, if you would register at tbcbrinadd.com on the events page. If you are registered for this presentation, you will get a replay and also an invite for our other 2 webinars coming up. Thank you so much for your time. If you have any questions, comments, please mark in the chat section or questions down below. We'll respond and reach out to you via email after the presentation. You can always reach Kim Tresco, Product Line Manager at ktresco@tbcbrinadd.com, and Mark Luyster is mluyster at tbcbrinadd.com to talk more technical. Your sales and marketing team is always here for you at salesandmarketing@tbcbrinadd.com. Thanks again so much for your time. Have a great day, and we'll see you next week for our loss circulation.